In the 17th century, Sir Isaac Newton wrote one of the most important science books in history, the Principia. It included Newton's laws of motion, formed the foundation of classical mechanics, and most importantly, his law of universal gravitation. This law stated that all objects attract each other with the force of gravitational attraction. Math worked. The formula described the movements of the planets and how they orbited around each other. But there was a problem. A few, actually. According to Newton, planets moved around the sun in elliptical orbits, but Mercury's orbit showed a deviation that Newton couldn't explain. And yes, Newton's law of gravity united the physics of falling apples with the movements of planets and stars under the same formula, but he couldn't explain how. How did gravity work? How did a star like the sun exert a force that pulled the Earth into an orbit even though there's just empty space between them? This mystery took almost 300 years and an Einstein to unravel. Einstein found that the ellipses in which the planets are moving are not immobile. They're also moving in space, which makes them deviate. The effect is stronger when the planet is moving in a stronger gravitational field, which is why the strongest effect is observed on Mercury, the closest planet to the Sun. But why were the orbits of the planets moving? Einstein explained this in 1915 with his brilliant theory, the general theory of relativity. Einstein thought of space in 4 dimensions. Our usual 3 axes, x, y, z, and time, collectively named spacetime. According to his theory, heavy objects in space, such as planets, bend spacetime around them, creating the orbits that we observe today. So the planets did not pull on each other. They simply fell into orbit around heavier things because of the curvature in spacetime. That's also why Mercury's orbit shows precessions. Einstein also predicted that, like all things in space, light would also bend towards heavier objects. To prove general relativity, he said, we must observe the stars on the night of a full solar eclipse. He predicted that the light would bend around the sun, making stars appear closer than they actually are. He was proven right in 1919 when astronomer Arthur Eddington took pictures of the stars during a full solar eclipse. Einstein's theory of general relativity predicted the existence of many things before there was any evidence, such as black holes, wormholes, and even the theoretical possibility of time travel. It also predicted the existence of gravitational waves, ripples in the fabric of space-time caused by the movements of giant objects, which were observed almost a century later. So the next time you see an apple fall from the tree, you'll know 2 things. 1, it's the curvature of space-time that makes the apple fall, and 2, it doesn't fall very far.